For a century, physics limited train speed through friction and air resistance. China just eliminated both. Their new train travels at 1,000 kilometers per hour, faster than a Boeing 737. Ground transportation will never be the same. The friction barrier. Every time steel wheels contact steel rails, energy converts to heat and noise rather than forward motion. At 400+ kilometers per hour, this friction generates enormous forces wearing down wheels and tracks rapidly, requiring constant maintenance. Engineers minimized friction through precision manufacturing and specialized materials. But they cannot eliminate it entirely. Wheels must touch rails, or trains cannot move. This fundamental limitation has constrained rail transportation for over a century, creating an effective speed ceiling no conventional technology could breach. Conventional speed limits. China's CR-380A reaches 420 kilometers per hour in testing. Impressive speed requiring years of engineering refinement. Its aerodynamic nose, inspired by fighter jet design, cuts through air resistance like a blade. The CR-380A demonstrates remarkable endurance, maintaining over 350 kilometers per hour for hundreds of kilometers without mechanical degradation. Advanced cooling systems using specialized fluids prevent engines from overheating during extended maximum power operation. It receives electrical supply continuously while moving, eliminating technical stops during long journeys. Yet despite these innovations, the CR-380A has effectively reached the practical speed limit for conventional wheeled trains. Japanese precision. Japan's Shinkansen E5 exemplifies the perfection of conventional rail technology, reaching 320 kilometers per hour commercially. Its true achievement lies in reliability rather than raw speed. The average delay across the entire Shinkansen network is merely 18 seconds per year, nearly impossible punctuality given modern rail system complexity. Each component functions with Swiss watch precision. Artificial intelligence detects and prevents problems before they occur. Maintenance is so meticulous that parts are replaced before showing the slightest wear. The Shinkansen's 60-year operation without a single fatal accident represents the safety pinnacle for conventional high-speed rail. Yet even this masterpiece of engineering cannot escape fundamental physics. At speeds above 350 kilometers per hour, wheel-rail friction becomes increasingly problematic. The solution requires abandoning wheels entirely. The air resistance problem. Italy's L0 Maglev demonstrates sophisticated approaches to atmospheric drag, reaching 360 kilometers per hour through intelligent aerodynamic design. Unlike traditional trains with locomotives concentrated at the front, the L0 distributes power throughout its entire length, allowing quicker acceleration and better space utilization. Ultra-lightweight materials reduce total mass, translating to lower energy consumption and higher speeds. Advanced suspension eliminates vibrations even at maximum velocity. Yet despite these innovations, air resistance remains insurmountable. At 400 kilometers per hour, approximately 80% of the train's energy fights atmospheric drag rather than propelling passengers forward. To achieve truly revolutionary speeds, engineers needed to eliminate not just friction, but air itself. Magnetic levitation breakthrough. The solution to friction emerged through magnetic levitation technology. Instead of wheels contacting rails, powerful magnets lift the train completely above specially engineered guideways. In China's electromagnetic suspension system, the train floats just millimeters above tracks, held by electromagnets controlled in real time through advanced electronics. This tiny gap, often less than 10 millimeters, is maintained through constant magnetic force adjustments responding to thousands of calculations every second. EMS technology relies on magnets positioned both above and below the train's guideway. By carefully tuning attraction and repulsion between these magnets and coils embedded in tracks, engineers can lift and stabilize trains weighing dozens of tons. System sensors and control units monitor the gap at microsecond intervals, making corrections to keep trains perfectly balanced even during acceleration beyond 600 kilometers per hour. With no wheels, there's no rolling friction. Only air resistance remains. Japan's Maglev record. Japan's L0 series Maglev demonstrates this technology's potential, having reached 603 kilometers per hour, currently the world record for magnetic levitation trains. Though not yet commercially operational, it's scheduled to enter service in 2027, transforming travel between Tokyo and Osaka. The journey, currently taking 2 hours and 15 minutes on the fastest Shinkansen, will be reduced to just 67 minutes. This revolutionary train uses superconducting magnetic levitation, maintaining a 10-centimeter gap above guideways without touching anything. The suspension system maintains perfect stability even at speeds exceeding 600 kilometers per hour. By floating completely, it eliminates friction and wear, allowing velocities no wheeled train could safely achieve. Yet even at 600 kilometers per hour, atmospheric drag remains the limiting factor. The vacuum tube solution. China's engineers recognized that magnetic levitation solved only half the problem. To reach truly extraordinary speeds, they needed to eliminate air resistance as well. Their solution: place maglev trains inside tubes where air pressure has been dramatically reduced. This principle mirrors what allows spacecraft to travel at extreme velocities. Without air creating drag, acceleration can continue to far higher speeds. The T-Flight Maglev operates inside these low-pressure tubes, combining magnetic levitation's frictionless motion with vacuum conditions that eliminate atmospheric drag. The result is unprecedented. Speeds reaching 1,000 kilometers per hour, surpassing the cruising speed of Boeing 737 aircraft, which typically fly at approximately 885 kilometers per hour. This achievement represents the culmination of decades spent understanding and overcoming the physical barriers that limited conventional rail. The practical implications are transformative. This system could theoretically cover the distance between Beijing and Shanghai in less than 2 hours, a journey currently requiring 4.5 hours on the world's fastest conventional high-speed trains. Ground transportation suddenly becomes competitive with aviation for distances up to 1,000 kilometers. Engineering the lightweight revolution. Achieving these speeds required solving problems far beyond those facing conventional rail designers. To reach extraordinary velocities, every gram counts. Chinese engineers turned to carbon fiber bodies and lightweight superconducting magnets, reducing train mass while maximizing magnetic field strength. The carbon fiber shells flex within safe limits while remaining rigid enough to maintain structural integrity at speeds where atmospheric pressure differences become significant forces. Japan's experimental Shinkansen Alpha X demonstrates similar weight reduction principles through different technology. This 10-car, 320-meter machine reaches 400 kilometers per hour in tests, employing monitoring systems analyzing more than 10,000 different data points while traveling. Its most striking feature is an extremely long 22-meter nose, designed like a spear tip to pierce through air without resistance. Revolutionary is that it can adjust configuration while moving. Sensors across its surface detect strong winds or pressure changes and automatically adjust position to maintain extreme speeds without losing stability. The emergency braking system can completely stop the train from 400 kilometers per hour in just 2 minutes, surpassing all world safety standards. The breakthrough test. On a humid morning at the Qingdao test site, engineers gathered in the control room, eyes fixed on monitors. The prototype Maglev, built with carbon fiber shell and loaded with sensors, waited at the track's far end. Lead engineer Dr. Liu from Southwest Jiaotong University recalls the tension before the run. The previous month, a resonance issue had forced emergency shutdown at 590 kilometers per hour. After weeks recalibrating coil arrays and refining active damping systems, the team prepared to push beyond 600. The train accelerated with a low, steady hum, gliding above the guideway on a magnetic cushion. Within seconds, the digital speed readout climbed past 600 kilometers per hour. Data streams showed vibration levels holding steady, the carbon fiber body flexing within safe limits. In the control room, a technician shouted as the counter ticked past 605, then 610. The run ended with smooth deceleration, all telemetry in the green. This test confirmed that the combination of magnetic levitation and reduced atmospheric pressure could achieve what conventional technology never could: speeds genuinely competitive with aviation. The passenger experience. A journey between Beijing and Shanghai by vacuum tube maglev promises experiences fundamentally different from both conventional rail and flying. Instead of long drives to airports and security lines, passengers board in city hearts. The train glides from stations, accelerating with gentle pushes. No jolts, no sudden climbs reminiscent of aircraft takeoff. At full speed, rides are almost silent with barely hints of vibration beneath seats. For trips under 1,000 kilometers, city-to-city connections erase hidden hours spent on ground transfers and boarding procedures. On Tokyo to Osaka corridors, studies show Maglev's door-to-door time can rival or beat fastest planes thanks to direct downtown access. Comfort inside matches speed outside. Steady pressure, no turbulence, and smoothness that turns high velocity into an afterthought. Environmental impact. Measured by carbon output, differences between Maglev and air travel are striking. On current test runs, China's Maglev trains generate an estimated 10 to 25 grams of CO2 per passenger kilometer. In contrast, short-haul jets on routes like Beijing to Shanghai typically emit between 90 and 130 grams per passenger kilometer. These numbers depend on factors like train occupancy and renewable versus fossil fuel grid mix. But even under conservative assumptions, Maglev's footprint is a fraction of aviation's. As China's grid shifts toward more renewables, the emissions gap will only widen, offering concrete bases for comparing climate impacts of future transport networks. For nations committed to reducing transportation emissions while maintaining high-speed connectivity, Maglev represents a viable alternative to expanding short-haul aviation. The challenges remaining. Vacuum tube Maglev promises speeds once reserved for science fiction, but engineering reality is far more complex than test-track demonstrations suggest. Building and maintaining near vacuum tunnels hundreds of kilometers long demands unprecedented precision. Each segment, often 6 meters in diameter, must align within millimeters to prevent leaks that could compromise entire systems. Energy required to sustain low-pressure environments and keep superconducting magnets cold adds layers of cost and complexity. Land acquisition along busy corridors has sparked disputes with local governments and property owners, raising questions about social and financial feasibility. Safety certification for passenger travel at 1,000 kilometers per hour remains undefined, with no published protocols for emergencies or rapid decompression inside sealed tubes. These aren't insurmountable obstacles, but they explain why vacuum tube Maglev hasn't immediately replaced conventional high-speed rail. The technology works in controlled test conditions. Scaling it to national networks serving millions of passengers requires solving engineering, regulatory, and economic challenges that will take years to address fully. In 2021, China's Maglev prototypes surpassed 600 kilometers per hour on Qingdao and Chengdu test tracks, marking new chapters in high-speed ground transport. Engineers achieved this by combining electromagnetic suspension with lightweight carbon fiber bodies and superconducting magnets, reducing friction and drag to near zero. While public records confirm test speeds above 600 kilometers per hour, claims of 1,000 kilometers per hour remain limited to controlled laboratory conditions. With no independent verification of sustained passenger carrying capability, what is clear is that China's Maglev program stands at the forefront of engineering ambition, setting new benchmarks for speed and sustainability in transportation. The question is no longer whether these trains will replace airplanes for medium distances, but how quickly it will happen, and whether the rest of the world will keep pace with Chinese innovation. Would you travel at 1,000 kilometers per hour on land? Share your thoughts below, and subscribe for more coverage of transportation innovations, reshaping how humanity moves across the planet.